Today we are going to look at Lesson 1, the fundamental counting principle. To begin, we will investigate the number of possible ways we can order a three-piece meal that includes a sandwich, beverage, and dessert. Number 1. A cafe has a lunch special consisting of an egg or ham sandwich, milk, juice, or coffee to drink, and yogurt or pie for dessert. We denote each choice by an appropriate letter as indicated in the diagram. One item is chosen from each category. We want to list all possible meals. We will write a series of 3 letters, the first for the type of sandwich, E or H, the second letter, M, J, or C, for the type of beverage, and the third letter, Y or P, to denote the type of dessert. Try to write these out in a logical sequence. Now, how many possible meals are there? We can just count, and we will see that there are 12. But a quicker way is to look at how many options we have for each choice. In this case, we have 2 choices for sandwiches, 3 choices for beverages, and 2 choices for dessert. So we have 2 times 3 times 2, which also equals 12 total possibilities. So, how can you determine the number of possible meals without listing all of them? Well, just multiply the number of options that you have for each choice that you need to make. Okay, another example from the same cafe, but this time we're going to have an ice cream cone. Question number 2. The cafe also features ice cream in 24 flavors. You can order a regular, sugar, or waffle cone. Suppose we want to order a cone with 2 scoops of ice cream. How many choices of cone do you have? Well, you can order a regular, sugar, or waffle, so 3 choices. How many choices of ice cream do you have for your first scoop? Well, there are 24 flavors, so 24. How many choices of ice cream do you have for your second scoop? Well, there are 24 flavors, and no reason why we couldn't have the same flavor as before, or try something different. So, 24 again. How can you determine the number of possible cones without listing all of them? We have 3 decisions to make. And it's going to be 3 times 24 times 24, which makes 1,728. Just something to think about. What if we had to have 2 different flavors of ice cream? How would our answer change? Just think about it. Let's try example 1. A computer store sells 5 different computers, 3 different monitors, 5 different printers, 2 different multimedia packages. How many different computer systems are available? We have 4 decisions to make. The first, how many different computers? 5. How many different monitors? 3. Number of printers? 5. Multimedia packages? 2. What do we do with these numbers? We multiply. So 5 times 3 times 5 times 2 gives us 150 different computer systems. Now it is time to define the fundamental counting principle. If one item can be selected in m ways, and for each way a second item can be selected in n ways, then the 2 items can be selected in m times n ways. Example 2. How many different 2-digit numbers are there? We often deal with questions that we do have to make a few assumptions for. For this, we will assume that a number can't start with 0. For example, 02 would not be considered a 2-digit number, but is really a single-digit number, 2. So our first digit can only be the numbers between 1 and 9. The second digit can, however, be any digit, including 0. This means there are 9 choices for the first digit and 10 choices for the second digit. Altogether, 9 times 10 gives us 90 two-digit numbers. Example 3. In each case, how many two-digit numbers can be formed using the digits 0, 1, 3, 5, 7, and 9? For part A, we are going to allow repetition. This means numbers like 55 and 99 are okay. Remember that a two-digit number cannot start with 0. The first digit can be 1, 3, 5, 7, or 9, which makes 5 choices. The second digit can be the same 5 digits from before, plus we could also have 0, for a total of 6 possibilities. We multiply 5 times 6 and we get 30 different two-digit numbers using 0, 1, 3, 5, 7, and 9. For part B, we have been given a restriction. Repetitions are not allowed. So now, numbers like 55, 99 are not allowed. So what do? Well, just like in A, we have 5 possible numbers for the first digit. But for the second digit, 0 is allowed, but whichever number was put in the first place can't be repeated. So we can only choose from 0 and the 4 numbers that were not used. So now we have a possibility of 5 numbers in that second spot. We multiply 5 times 5 to get 25 possible numbers where the digits don't repeat. Example 4. A true-false test has 7 questions. Suppose students answer each question by guessing randomly. This question is similar to ones before, but with a bit of a twist. We want to know how many different patterns of answers are possible. First, how many possible answers are there for each question? You have the choice of true or false, so 2. How many different patterns are possible for the answers to the 7 questions on the test? You have 7 different choices to make, 1 for each question, and 2 choices for each. So 2 times 2 times 2 times 2 times 2 times 2 times 2, which can be written as 2 to the power of 7. You can throw this in your calculator to get 128 possible patterns for this test. For C, I'm going to look a bit ahead to Unit 3. What do you remember about probability? What is the probability of a student answering all 7 questions correctly? Well, since there would be only one way to get all questions correct out of a total of 128 possible outcomes, the probability would be 1 over 128. Let's look at a similar question. Example 5. A multiple choice test has 7 questions with 4 possible answers for each question. Suppose students answer each question by guessing randomly. First, how many different answers are there for each question? In this case, 4. How many different patterns are possible for the answers to the 7 questions on the test? You now have 7 different choices to make, 1 for each question, and 4 choices for each question. So, it's 4 times 4 times 4 times 4 times 4 times 4 times 4, which, again, can be written as 4 to the power of 7. And this works out to be 16,384 possible outcomes. Now, what is the probability that a student answers all 7 questions correctly? Well, since there would only be one way to get all the answers correct out of a possible 16,384 possible outcomes, the probability would be 1 over 16,384. I don't think that's very likely. You have now completed Lesson 1. Now try the practice assignment. Full solutions are available by clicking on the key icon in your Blackboard.